We talked about flux in an earlier section when we were talking with electricity. Similarly, we can talk about magnetic flux as well. When we talk about magnetic flux, we're talking about the amount of magnetic field that flows through a surface and through some sort of surface area. So if I had a region of space here that had a magnetic field, and really, well, I should be consistent. So I'm not particularly concerned about what would create this magnetic field, just that there is a magnetic field in this region. So there's some sort of magnetic field in this region. If I had a small ring, so this ring would have flux flowing through it because there's magnetic field lines flowing through. The flux, sorry, I'm stumbling on how I want to say this. The ring has magnetic flux. It has magnetic flux because there are magnetic field lines that are passing through that area. The area is this circular area. So because magnetic field is passing through the circular area. Bounded by the ring. Okay, so flux is the flow or the passing of magnetic field lines here through a given area. I would have flux through another shape as well. I could take a square or rectangle here. This rectangle has flux as well. And that's because there are magnetic field lines passing through it. Now, this larger area of my rectangle allows more magnetic field lines to pass through. So the rectangle has more flux than the circle. And that's simply because it has a larger cross-sectional area, and that larger cross-sectional area allows for more magnetic field lines to pass through. Okay. Our fundamental equation for magnetic flux we're still going to use phi like we did before, but I'm going to put a subscript of m for magnetic flux. Magnetic flux is calculated by integrating the magnetic field as it passes through an area. If we have a region like I tried to represent in my picture, where the magnetic field is uniform, meaning it has the same value everywhere in the area at the same time, then we can pull b out of the integral Integral of dA is going to be the total area of that circle or ring or the rectangle. We can write this also as B magnitude of magnetic field times the magnitude of the area times the cosine of theta, where theta is the angle between the vector magnetic field and the area vector. Now, if you recall, area vectors are normal to the surface or the plane of the area. So coming back to our picture, the area vector would point with the magnetic field, either into the screen or out of the screen. When we talk about just a two-dimensional area like this, in or out, getting a positive or negative flux does not have any particular meaning. It's not until we talk about Gauss's law that the area vector has to point outwards, away from the center of a closed surface. So the area vector is normal to the surface, so pointing perpendicular to the surface itself. Now the units of magnetic flux, well, magnetic field is in Teslas, so capital T. Area is going to be meters squared when we're talking about SI units. So Tesla meters squared are the units of flux. We also call this a Weber, just like Weber state, but we pronounce it Weber. I believe they abbreviate that sometimes as a WB. So magnetic flux, the flow of magnetic field through a surface. Oh, excuse me. Sorry for the jump in size. I was copying a picture in. I paused to do that. And I'm also recognizing I didn't write this right, magnetic flux. Apologize for that. I wanted to bring in a picture where we can talk about magnetic flux a little bit more. So this rectangle down here represents our area that will have flux. B, this arrow is representing that we have a magnetic flux, and we're going to assume we have this magnetic field everywhere in this region. So something is creating this magnetic field that makes an angle such that it points to the left and upwards. The dotted line represents the normal vector, meaning perpendicular So this is the direction that the area vector will point in, perpendicular to that rectangle. So theta in this picture is what we mean by theta in our equation for flux. Now, if we think about cosine of theta, if we are talking about B at this angle, and theta is right here, this magnetic field vector has a component that points straight upwards and a component that points to the left. That would be a B sine theta term. It's only this component of B cosine theta that is actually passing through the area. The X components, the components that are parallel to the surface, these do not pass through. And so they are not part of the magnetic flux. And that's why we end up with the magnetic flux being the magnitude of the magnetic field times the magnitude of the area times the cosine of that theta, because that gives us the component of the magnetic field that passes through the area. Now, magnetic fields do not need to be uniform across the area. If the magnetic field is not uniform, then we need to integrate. So an example of that, let me slide this to the left. If I had a long wire that was carrying current, I know this wire would be creating magnetic field lines that wrapped around it. So if I was talking about some sort of rectangular surface, just to be on the simple side, over here, I know there would be magnetic field lines pointing in. And that's going to be true throughout the entire area of this rectangle. But the magnetic field here along this line is stronger than the magnetic field. Oh, that wasn't a big difference in color. Sorry. Let me draw it a little bit differently. So the magnetic field, as we get further away from the wire, the magnetic field gets weaker. And so to represent that in my picture, I would draw fewer lines. And by the time we're over on this far side, there's still magnetic field into the screen, into the screen, but it gets weaker and weaker the farther away we get from the wire. So if you recall, B of the wire, mu naught I over 2 pi d is how we have that written in our test notes. Now I'm going to write it as a R instead, meaning the strength of the field depends upon how far in this radial direction away from the wire. And so the magnetic field is strongest in the left side of this rectangle compared to the right side. So if we wanted to find the flux, the area vector for this rectangle, well, let's call this the width. This would be the length. So width and length. The area would be length times width. The direction of this vector, I'm going to just make it into the screen as opposed to out. I know it's parallel to the magnetic field. Okay, we do need to integrate to find this magnetic flux. So the magnetic flux will be the integral of B dotted with a dA. So we need a way to figure out a dA, meaning we need to choose an area such that the magnetic field is uniform in that area. And then we're going to add up all the B dot dAs. The area I'm going to choose is going to be a rectangle. So here, I know that any portion of this that is the same distance away from the wire has the same magnetic field in it. Okay. So the area, I'm going to call this a dA, an infinitesimally small area. where the magnetic field is uniform. Okay, I need some sort of width. I'm going to call that dr. So if I could zoom in on that little rectangle I'm drawing, since I'm calling the distance from the wire out to any one point r, I can call the width of this infinitesimally small piece dr. But because every single point that is the same distance away has the same strength, I can take that whole strip with length L. And so my dA would be that width, this dr, so the infinitesimally small little width, times that entire length or height, and get the area of this really tiny, thin rectangle. The direction of this is going to point into the screen. What I need to do is to plug that in. Since B and dA are parallel, we're going to get the integral of B dA, just the magnitudes, because the angle between them is 0, so cosine of 0 is 1. I need to put in my equation that describes the strength of the magnetic field, and then my A. dr needs to represent from some distance. Let me redraw my picture. So if this is my wire, here is my rectangle. My limits of integration need to be between where the left edge of my rectangle is, I'm just going to call that A, to where the right edge of my rectangle is. So R equals A to R equals B. We're essentially saying we're adding up these vertical strips between a location of A and B. The current does not change with a distance R. The current is whatever the current is at the moment we're talking about. So however many amps. L is this height or length of the rectangle. So I can pull those out. I can pull the 2 pi out. That leaves me with 1 over R dr, evaluated between A and B. So mu naught I L over 2 pi. Integral of 1 over R is natural log. So we get natural log of B minus natural log of A. So the magnetic flux through that rectangle ends up looking like this. And again, we had to integrate simply because the magnetic field is stronger in the sections that are closer to the wire than in the sections that are farther from the wire. So integration has to be done if the strength of the magnetic field is different in different parts of the area. If the magnetic field depends upon a distance, then we have to integrate to find this flux. But if it is not dependent upon distance, if that magnetic field has the same value everywhere in the area, like this original picture, if that magnetic field was uniform, then we can look at just B dotted with A. We don't have to integrate. Okay, so that's for magnetic flux through just some sort of two-dimensional surface, which we're actually going to build on in the next video. But I want to mention first Gauss's law. If you recall electric flux, Gauss's law talked about the flux through a closed surface. We wrote the integral with the circle on it. That's what meant the closed surface. And we found that the overall flux through a closed surface, when we're talking electric flux, it ultimately boiled down to depend on just the charge enclosed by that surface. Nice and simple. If we want to talk about the magnetic flux through a closed surface, this is still considered Gauss's law, but Gauss's law for magnetism. We would put a circle on the integral, meaning the same thing. Okay, let's think this through for just a second. With electric flux, that meant if I had a charge, just for simplicity's sake, positive Q, that means if I put a closed surface, like a box, the flux through this closed surface, electric flux, was simply equal to that charge divided by our constant epsilon naught. If I chose a circle, or rather a sphere, so that it was a closed surface, the flux through this was that charge divided by epsilon naught. The shape of the closed surface didn't matter. If I have a positive net charge inside the surface, I will have more electric field lines pointing out than pointing in. And that's why flux simplified so nicely to be the charge enclosed over epsilon naught for electric flux. Well, magnetic flux. Let's think about a bar magnet. North end, south end. We know the magnetic field points out of north, wraps around, comes back into south, continues inside south to north. The magnetic field is always continuous, regardless of what's creating it. There's no start or end to the magnetic field. That means any shape I choose to draw that is closed will always have the same number of field lines coming out of the surface as going back in to the surface. Which means Gauss's law for magnetism is always equal to 0. This is specifically to a closed surface. Now, in and of itself, this just tells us that magnetic field lines are continuous. There's no such thing as finding a magnetic north pole by itself. Okay, so we cannot use Gauss's law to find B in certain situations. So we will see Gauss's law again because it's one of Maxwell's equations, which may or may not mean anything to you right now, which is fine. But this concept of flux in general, not through a closed surface. Magnetic flux through an open surface. So a rectangle, something like that, not closed. This concept is extremely important because it leads us to induction. But flux in and of itself doesn't give us this induction. we find that if we can change the flux, we can induce a voltage. So we're going to talk about Faraday's law. Changing magnetic flux induces a potential difference, an EMF. If there is a complete path for charges to move through, it induces current. We can get current flowing simply by changing magnetic flux. So I'm going to link to a couple of videos, and we'll talk demonstration videos so that you can kind of see this. And then we'll also talk about the equations that describe Faraday's law.